Right. Today I released a new package, which is Gorgonia, and it's basically a library that provides primitives for dynamically building neural networks in Go. You can think of it like Theano or TensorFlow, but it's written in Go. And the main reason why I did that was because when I started with this project, Theano was a pain in the ass to deploy in the cloud. It probably still is a pain in the ass to deploy Theano in the cloud today. And TensorFlow had not come out yet. In fact, today you still cannot use TensorFlow if you're using Go, right? So very briefly, what is Gorgonia? It's basically that. So we'll walk through some examples of how to build a neural network. So we'll build first an expression graph. Think of it as an AST, abstract syntax tree for your neural network. And then you compile that into a program and it runs in a VM. That's pretty much the basic details of how it works. So we'll start by building an expression graph. We define a new graph, and we'll say X is a matrix with the shape of 5 and 5. W is a vector, weight vector with shape of 5. XW is multiplication of X and W. And the activation is the sigmoid function of the multiplication. Now, if this formula seems a bit familiar, it's because it's the sort of most basic neural network that you can build. That's a single layer, single fully connected layer. And here's a refresher. You've got your input nodes, your activation level, and the output, right? So this is a 3-layer neural network. This is X. This is W. You combine them both together, it's a multiplication of X and W. And then you run the activation function, the sigmoid function, and there you have it. That's one layer of your neural network done. Now, that was a symbolic graph, okay? So you're just telling, this is a program that you're going to run. We'll provide the input later. And this is how it looks like. This is an actual output of Gorgonia. It says XW, multiply, and sigmoid. You can actually print all these graphs. And the thing about neural networks is when you learn a neural network learns the values of W by doing backpropagation. And backpropagation is just simply differentiation across from the end all the way back to the front. That's it, right? So if you've got an expression graph, you can differentiate this graph. I've been writing backpropagation manually for ages. Then I discovered that you can actually write an automatic differentiator, and so I did. So to do symbolic differentiation, it's simple. You just make it a cost. You sum the activation, and then you call the grad function, and grad's O is d cos dw. Yeah? Okay. And then you've got the full graph inclusive of the differentiation. So now you've got to execute the graph. And the package comes with 2 different types of VMs, the tape machine and the list machine. And they were basically created for different purposes. There was a third VM that used stacks and dealt with artificial gradients, but Google Brain came up with something significantly better. So, the tape machine is basically your standard, what you expect of a VM. You give it a graph, it compiles out into a linear program, and it runs it. So it's optimized very well for compile once and execute many times kind of programs. Well, the list machine is actually you provide it a graph, and it just walks the graph and executes the graph as it goes along, right? So we'll see an example of using a tape machine to execute a graph. So first you compile the graph into a program and a location map. Then you have create a machine. Then you tell the machine that, hey, X is this value, W is this value, and then you run it. That's it. And of course, I have to compare this with Theano. In Theano, it's just these small functions, but in Gorgonia, it's actually kind of longer and more verbose. But call it a biased opinion. I think that the more verbose version allows you more mental clarity of how the thing is actually run. Plus, you get to debug the program. This is the actual program that is generated. It says first you load these instructions into the register, register 0, register 1, and then you allocate all these things, and it just executes. So when the error comes back, it comes back with which instruction failed, where, and why it failed. If there are errors in the program, usually that's because it's some kind of weird NaN, not a number or infinity kind of errors. So things that you can do with Gorgonia. I did this thing where I took a bunch of music from a bunch of composers, I fed it into a neural network, and it automatically composed music being based on, being inspired by these people. You can build a neural tensor machine. Bear in mind that these things were built with a previous version of it, which is a lot more, it's a lot more sort of private stuff on it. And of course, you've got the not so cool stuff as well, the original machine learning algorithm, linear regression, for example. Yeah. There are things that Gorgonia cannot do yet. Convolutional neural networks. I've somehow never got the interest to do sort of image processing for neural networks, so I never wrote any ops for it. And the reason why this this lightning talk is held, because I want you to help with Gorgonia, right? The test coverage is abysmal. It's at 50%. It's crap. When I ported this package over to the public repository, I discovered some weird assembly bugs with float32 slices. I've still not figured that out yet. But the previous version did run very, very well with AVX float32s. So yeah, check it out and help me out. That's all. Also, guys, I'd like to say a lot of thank you to Tim, who has put in a lot of effort for today's video streaming. Pivotal for hosting us, and right. We've got our three sponsors: Identity, bgraph, and Naviro. Thanks for them providing surprisingly bachelor food, which is what you usually get at meetups like pizzas and beers, but this is surprisingly non-bachelor food. So yeah, thank you. And thank you all, most importantly, for coming. Hope to see you guys next month. And if you guys have interested in talking, please look us up. Thank you.